So just to remind us a little bit about function algebra, we were doing this earlier, but we have a couple of ways that we can combine functions, right? So we have f plus g of x, we have f minus g of x, we have f times g of x, and we have f divided by g of x. And we're going to build on this idea, and as we saw for function algebra, it means, like f plus g means exactly what we think it does. It means f of x plus g of x. F minus g of x means f of x take away g of x. F times g of x means we are going to multiply the two functions together. And lastly, f divided by g means that we are going to divide them. Once again, with the one restriction that g of x cannot equal to the number 0 because we are not allowed to divide by 0. So function algebra tells us that we are just going to perform the indicated operation on whatever functions we were given. Well, let's go ahead and take a look at a couple of our examples. So we wish to find f plus g of x given f of x is x plus 7 and g of x is x squared minus 3x. So by our definition, f plus g of x is going to be the same as f of x plus g of x. And then we are given explicitly what each of these functions are. So f of x is x plus 7 and g of x is x squared plus 3x. So this is going to equal to x plus 7 in parentheses plus our g of x, which is x squared minus 3x. So then we just collect up our like terms to get our new function f plus g of x, which would be equal to x squared. And then we have x take away 3x is negative 2x plus 7. That would be our new function f plus g of x. So the next part says, given that, we want to calculate f plus g of 2. Well, we're going to use the exact same function that we had. So we have f plus g of 2, and this behaves just like a regular function. So now it's telling us to go to our function f plus g. Well, that's right here. And we're going to replace all of our x's with 2. So that would give us 2 squared minus 2 times 2 plus 7. So 4 minus 4 plus 7 would give us 7. It's also worth noting that we've created a new function f plus g, but let's calculate f of 2. Well, f of 2 would be 2 plus 7, which is 9. And g of 2 would be 2 squared minus 3 times 2, which is 4 minus 6, which is negative 2. And if I add f of 2 to g of 2, I would get 9 plus negative 2, which is also equal to 7. And we get the same value, right? So the idea of function algebra is whether we evaluate the functions first and then perform the operation, we will get the same output as if we do the function addition or subtraction or whatever first and then evaluate the new rule that we have after. So there are pros and cons to both methods. Oftentimes, the big idea behind this is when we're trying to model something in real life, trying to model a very complicated situation would involve a lot of functions. It's often easier to break a problem down into simple parts, solve each of those parts, and then use function algebra to assemble your final answer in the end. We will do some examples of that a little bit later. But that's really the big idea of what we're shooting for with this. So we can do the same thing with our next two examples by just calculating our values. So given that f of x is equal to the square root of x minus 7 and g of x is equal to 3x plus 2, find f times g of 2. Well, f times g of x is going to be f of x, which is x minus 11, in the square root, times g of x, which is 3x plus 2. Then f times g of 2 is going to be the square root of 2 minus 11 times 3 times 2 plus 2. Well, 2 minus 11 gives us negative 9 under the square root, and this is not a real number. So, in terms of our function algebra, since that's not a real number, the value of f times g of 2 is not a real number. Similarly, we got to be a little careful with example number 4, because if we go f divided by g of x, that is x squared minus 1 all over x minus 1, and you might be like, well, that's the difference of squares, so that's x minus 1 times x plus 1 all over x minus 1, and then our x minus 1s reduce out, giving us f divided by g of x is equal to x plus 1. And then we might think, oh, I can plug 1 in to that function, f divided by g, and if I try to evaluate that at 1, I get 1 plus 1 is 2. But we have to be careful, because if we look at our original function before we simplify, what would happen if we tried to put 1 in? Well, we would get 1 minus 1 in the denominator, which is 0. So f divided by g is undefined at x equals 1. So we have to be a little careful when we're looking at these problems. And make sure that we don't simplify too much before we attempt to work these. Now that we've reminded ourselves a little bit about function algebra, we want to talk about what the real main goal of this section is, which is function composition. So composition is a new way for us to combine two functions. So we've talked about adding, subtracting, multiplying, and dividing using our normal rules of algebra. So function composition is a new way to combine two functions. So let's start by drawing a picture to help us visualize what's happening. So each of these circles represent domains and ranges. So if I visualize this circle as the domain of some function g, and I visualize the circle in the middle as the domain of some function f, but also as the range of g, then g would take elements from its domain to its range, and then we could also have our function f take elements from its domain to its range, and so that would be our rule f, and this would be our rule g. The idea of function composition is going directly from the domain of g to the range of f. So this is function composition. So we could chain two functions together by putting something into g, getting its output, putting the output of g into f, and then getting to the range of f. but it is desirable often to skip that whole process in the middle and go directly from the domain of G to the range of F. So before we dig too much into this, let's talk about our notation and symbols. So the composition symbol is a circle centered on the line, and mathematicians in their infinite wisdom named that symbol circle. So f circle G of x is defined to be the function f evaluated at G of x. So this is read as f circle G of x, or f composed So when we have f circle G of x, it means we are going to input the function G into f. So this symbol means, just like what we were doing earlier when we found f of 2, we're going to replace each x in f with G of x. So we are going to input a function into another function. So now, let's go ahead and look at example number 5. So consider the function f of x equals negative 0 or negative 0.008x plus 96.898, where x is the height above sea level and f of x is the percent oxygen compared to sea level. The maximum rate of ascent for an F-15E is 254 meters per second. If it is flying at 350 meters per second and starts climbing at its maximum rate, write a linear function for its height. Use t for time and g of t for the height. All right, so if we have our function g of t is equal to mt plus b, our slope is going to be our rate of change. So that would be the maximum rate of ascent, so 254 meters per second. And our starting value is the height when this begins, which is going to be 350 meters. So our function becomes 254t plus our starting value, which is 350. So now we have two different functions. We have f of x and we have g of x. So let's do a little bit of analysis on each of these. So the input for f is what? Well, we're inputting x's, but what does x represent? Where x is the height. And then we have our output of f. So f of x, and what does it give us as an output? It gives us the percent oxygen. And now we have another function g. What is it that we're inputting into g? Well, we used t for that variable, and the input for g is time, and its corresponding output of g is going to be a height. All right, so let's keep going. Let's answer our next question. So the pilot may wish to know how much oxygen there is after she's been flying for, say, 5 seconds. So what is the oxygen available for there? We're going to compute this in two different ways. So what would be the altitude of the plane after 5 seconds? So which function would I use, f or g? I'm going to use g, because I input into g a time, so g of 5 seconds would be 254 times 5 plus r, 350. So putting that into my calculator, I'll go 254x plus 350. And I can calculate that by just putting in my 5. And I get 1,620. So our altitude of the plane would be 1,620 meters after 5 seconds. All right, so then the next question we want, which is the answer to the original query, is, well, how much oxygen is there available now? Well, now we have the output is 1,620 meters. Well, that's a height, which is going to be the input for our function f. So if we calculate f of 1,620, we're going to put that into our function. So let's put our function f in as y2 in our calculator. So we go down to y2, we have negative 0.008x plus 96.898. And then we want to evaluate that value. So alpha trace, and we select y2 this time, and we're going to put in 1,620. So we get 83.938. And this, the output of f is percent oxygen. So that would tell us that there was 83.938% of the relative oxygen at a height of 1,620 meters. So the air is a little bit thinner at that height. So this is similar to the idea of what we were doing up here, where we calculated two things separately and then combined them afterwards. The idea of function composition is we want to skip that whole idea. So function composition can be used to find a new function h of t that takes time as an input and outputs the percent of relative oxygen. So h of t is equal to f circle g of t, or f of g of t. Use this to find the percent relative oxygen after 5 seconds. So we have our two functions. We had our f of x was equal to negative 0.008x plus 96.898. And we had our g of t is 254t plus 350. we want to find our new function h of t, which is the function composition. So that's going to be negative. We're going to put g into f. And we're going to put this in to f everywhere we see an x. So we have negative 0.008 times g. It's g of t, add it right over there. G of t. So we get 254t plus 350, and then plus 96.898. So then if we multiply that out, we're going to get negative 0.008 times 254 gives us negative 2.032 t, and negative 0.008 times 350 gives us negative 2.8. Plus 96.898. So plus 96.898, and we get 94.098. So our new function, represented by the composition, h of t, is negative 2.032t plus 94.8. And if we calculate h of 5 now, we'd have negative 2.032 times 5 plus 94.098. Negative 2.032 times 5 plus 94.098, and we get 83.983. And we'll notice that we get the same value we got when we did the two computations separately. So once again, it gives us the percent oxygen. But our new function h, what is our input into the function h? Well, our input variable is t, which is time, and our output of h is then going to be, as we just got, the percent oxygen. So explain why the function composition g circle f of x does not equal f circle g. Think about the units of each. So we'd written down earlier what the units were for each. So the input for f was an x, which was a height, and its output was an, I don't think I'm right. Yeah, output was a percent oxygen. And our input for G was a T, which was a time, and our output of G was a height. So if I think of what f circle g of x means, by unpacking this, on the inside, this is the input of g. And what is the input of g in our case? Time, and then g itself, the whole thing, what is its output? A height. Well, that's good, because what does f expect for its input? It wants a height. So this makes sense, because the input of f is a height. But if we were to turn this around the other direction, what is our input for f? Well, the input for f is a height, and our output for F is a percent oxygen. But what does G expect for its input? G wants time. And these two things are not the same. And that's really the problem. In this specific case, we had units attached, which makes it quite obvious that these two things can't be equal. Because our function g needs to have an input of time, but our function f has an output that is in height. So those inputs and outputs aren't compatible. So going back to our original diagram, it gives us some context to this. So what's happening with our diagram, and what we're seeing is, we have the domain of f in the range of g, but they're not necessarily always going to be the same, right? So it's entirely possible that those two things are not the same, and in fact, there's only some subset of the domain of g that would map into the domain of f. And this gives rise to the big idea, which is we may need to restrict the domain of g so that the range of g is in the domain of f. So the case that we did, we had units that helped us reinforce it, not just an abstract mathematical way of thinking, but that's still going to be an issue where we have to make sure that the range of g and the domain of f have a non-empty intersection. That is, that there is some target point in the middle. A good analogy to help you make sense of this is visualize each of these three circles as an airport, and you're trying to get to New York. So you fly from Phoenix, which is here, to Atlanta here, and then from Atlanta to New York City, right? But it might be desirable to go directly from Phoenix to New York City. You wouldn't want to stop at an airport that didn't fly to your final destination. So if you flew from Phoenix to San Diego, but San Diego does not fly to New York, then we would have a problem. And that's really what we're talking about here. So we're going to dig into this a little bit more deeply in just a second. Well, let's practice some mechanical stuff involving function composition. So let's take a look at each of these. So given that f of x is 1/2 x plus 4 and g of x is 2x minus 8, find g circle f of x and g circle f of negative 2. So when we have function composition, it's always the second function is going into the first function. So when we write g circle f of x, that means we are going to be putting the function f into the function g. So in this case, we're going to be putting f into g, so we end up with the following: 2 times our f of x, which is 1/2 x plus 4, take away 8. Distributing our 2 into our parentheses, the 2 and the 1/2 reduce out. 2 times 4 is 8, minus 8, and we get x. So we get g circle f, which is our new function, is equal to x. So then g circle f of negative 2 is equal to negative 2. So just to verify, like we did with the function algebra, if I calculate f of negative 2, f of negative 2 is going to be 1/2 times negative 2 plus 4, which is going to be negative 1 plus 4 gives me 3. And g of 3 is going to be 2 times 3 take away 8. 2 times 3 is 6 minus 8 gives me negative 2, which is the same thing that I got when I did the composition and then evaluated, as if I did each of the computations individually, calculate f, find the output, take the output of f and put it into g, and get the corresponding value. All right, so to calculate f circle g, we are going to be putting g into f this time. So it's going to be 2 times x minus 3 plus 1, which give us 2x take away 6 plus 1, so 2x take away 5. So then f circle g of 3/4 is going to be 2 times 3/4 take away 5. So 2 times 3/4 is 3/2, and turning 5 into a fraction with a denominator of 2 is 10 over 2, so we get negative 7 over 2. So we can also use our graphing device to do some of these computations. So if we wish, we could put f and g actually into y1 and y2. So f is 2x plus 1, and g is x minus 3. And then we can make y3 represent the composition, because we want to put y2 into y1. So we go alpha trace y1 parenthesis alpha trace y2 parenthesis of x, close our x's. It's going to think for a second, and if we go second table now, we'll notice we have our xy tables, and if you scroll over to y3, we're going to see the output of the composition f circle g, because we put y2, which was g, into f. You can also do it in the other order to see those things. If we want to do some direct calculations, if we go into our table set menu by hitting second and then window, instead of having our independent variable on auto, we can change it to ask. After doing so, we go second table, and our table looks blank, and you're like, hold on, what the heck? So then we can go ahead and choose values to input. So if I go 3/4 for my input, I would see I get 5/2 would be the output of y1, y2 would be this, and then the composition would be negative 7 over 2, which is exactly the same thing that we got. You can also, I'm going to change my table back to auto, use the same thing on the home screen, right? So alpha trace, y3 represented our composition, so we could go ahead and input our value of 3/4 and get the same output of negative 7 over 2. So we can use our y, or our function inputs, to generate values or tables as needed for function composition. All right. Let's take a look at problem number 11. So 11 is given that f of x is 5 over x minus 3, and g of x is 1 over x. Find f circle g of x and find the domain of f circle g. So we've been doing the f circle g part, but we're going to have to do a little bit more work with our domain. So let's start with f circle g. Is going to be, we're putting g into f, so that gives us 5 over 1 over x, take away 3. And then we have a compound fraction, so we multiply the numerator and denominator by the LCD, which is just x in this case. And we get 5x. And 1 over x times x is 1 minus 3x. So f circle g of x is 5x all over 1 minus 3x. But now we need to find its domain. So if we were to just look at the simplified version that we have here, or even the one before it, what would we think the domain is? Well, we're not allowed to divide by 0, so what value can't x be? So x could not be 1/3, because the solution to 1 minus 3x equals 0 is 1/3. Unfortunately, that is incorrect. That is not the domain of f circle g. So let's go back to our diagram. I mentioned it in words, but now we'll write some stuff down. So we have this thing in blue happening. So what we're really concerned about is we may need to restrict the domain of G so that the range of G is in the domain of F. So that's really our key idea. We need to restrict the domain of G, so the range of G is in the domain of F. So in order to do this, the first thing we need to do is find the domain of G, because that's our starting point. So we look at G, and G is the function 1 over x. So what is going to be our domain of G? Well, we have a rational function, so the denominator cannot equal 0. And that happens when x equals 0. So x can't be 0, so that's not in the domain, so we get negative infinity to 0, unioned with 0 to positive infinity. The next thing we need to do is we need to find the domain of f. So f is also a rational function in this case, which is 5 over x minus 3. So we have that x minus 3 cannot equal to 0. So we add 3, and we get x can't be 3. So now a couple of things can happen. If the domain of f is all real numbers, the domain is the domain from step 1. If the domain is not all real numbers, we're going to go to step 3. And step 3 says find all inputs of G that are not in the domain of F. Let me make that a little clearer. Find all inputs of G such that g of x is not in the domain of f. So in our case, g of x this time is the function 1 over x. And what's the only point that's not in the domain of f? 3. So we need to find all points such that g of x is equal to 3. So we need to solve the following in this case. 1 over x is equal to 3. So we multiply by x, and we get 1 equals 3x. We divide by 3, and we get x is equal to 1/3. Then we remove all solutions from the domain from step 1. So our domain in step 1, if we did it on the number line, is we had the number 0 in the middle that was already excluded. And now we also have to remove the value we just found. In this case, there's only one of them. So we remove the value of 1/3 as well. So if we take those two values out, our domain goes from negative infinity to 0, unioned with 0 to 1/3, unioned with 1/3 to positive infinity. And that would be the correct domain of F circle G. So then notice if we just did the composition, we would miss one of the points that needed to be removed from the domain. So we can't just go to the answer and find the domain. It will unfortunately lie to us some of the time. So we have to actually figure out the domain and range of each of the functions and then combine them using this algorithm. Let's take a look at our next one. Given that f of x equals x squared minus 3 and g of x is equal to the square root of x plus 3, find f circle g of x and find the domain. All right, so we start off same way as before. F circle g means we're putting g into f, and that gives us the square root of x plus 3 squared minus 3. So the square root of x plus 3 squared is x plus 3 minus 3, and we get x. So looking at this, what might you guess the domain is? All real numbers, right? Is there anything you can't put into x? No. Well, let's check. So the first thing we do is we have to find the domain of g. And we have a radical function, so we have to solve the radicand x plus 3 is greater than or equal to 0. So we minus 3, and we get x is greater than or equal to negative 3. So our domain is from negative 3 to positive infinity for g. Step 2 said we need to find the domain of f. Well, the domain of f is going to be all real numbers because f is a polynomial. So polynomial. So the domain is all real numbers. So we get from negative infinity to infinity. We had a clause when we did step 2 that said, if the domain of f is all real numbers, the domain is just the domain we found from step 1. So since it's all real numbers, the domain is the same as the domain of G. So then that makes our domain the same as it was in step 1, which is this. So our domain would be from -3 to positive infinity. Yes? All right. So next thing we want to talk about is if we can do something in mathematics, we also have to be able to undo it. And we want to talk about decomposition. So decomposition is basically the inverse operation of composition. So to do composition, we replaced every x in f of x with g. So to undo that process, the first thing we need to do is identify the inside function which I will call g of x. And then step 2, we're going to replace g of x with x. Because composition says we replace every x in f with g of x. So to undo that, we have to figure out what g of x is, and then we replace all instances of g of x with x, because that is the inverse operation of what we did to do composition. So let's take a look at example 13. So find f of x and g of x such that h of x is equal to f circle g of x if h is equal to pi divided by 2x plus 5 cubed. So we need to look for something that is inside of something else. Well, we have a 2x plus 5, which is inside the cubing function. So that is our candidate for g of x. So if g of x is equal to 2x plus 5, to recover my function f, I'm going to replace all instances of g of x in h with x. So pi divided by, and the 2x plus 5 becomes an x cubed. And that would be my f of x. Because now if I replace that x in pi over x cubed with 2x plus 5, I would get exactly the function h. So I'm just running function composition backwards. All right, so to resolve this, we need to identify what's inside. So we notice that the x plus 5 appears inside in 2 different places. So that's going to be our candidate for g of x. So g of x is equal to x plus 5. So then replacing each of the g's with x gives me x to the 7th plus 3x plus 1. So then my f of x would be x to the 7th plus 3x cubed plus 1. And that would be my f when composed with g that would give me my function h.